Hi, I'm Sean Gannon, and this is Minute Math. And we have a figure here, geometry problem, and we want to find what the area of the circle is. A few things to note: we have a circle that's inside of a square. Okay, important to note here. And we have this rectangle here that goes right in the corner with a side length 1 and then 2. With just this little amount of information, can we determine what the area of the circle is? So I want you to pause, see if you can remember some geometry theorems here, and see if you can solve this problem. But as always, we're going to learn something here. I'm going to show you a way to solve this problem. Okay? So first things first, I'm going to do is I'm going to draw a vertical diameter. Okay, vertical diameter perfectly here through the circle. Okay, so go draw that here. Draw a diameter, and let's go label some points that happen. I'm gonna call this one A here, and I call this one, I'm gonna call it B. Yep, yeah, B right here. All right, and the center, let's just label that O. O right here. Okay. Well, one thing we know here is that a tangent to a circle theorem tells us that if we have a diameter or radius that's going, hits down to something that's a tangent to the circle, this line right here is, then it's gonna be perpendicular, and it happens up here. So we have little perpendicular lines right there that kind of, well, give us a little more clues to what's going on. From here, I am going to actually extend this line across. So I'm going to extend our current rectangle, okay? Remember, since it's a rectangle, we got a little 90-degree going on right here, okay? So I'm going to extend that so it goes all the way across this circle. Extend it right there, okay? And then with this, since our circle is going to be symmetrical within the square, we can draw the same exact figure, rectangle that we have right here. So draw a little line down right there. And what do we know about this? Well, if it's symmetrical, these squares will be the same size. We have a 2 here and 1 as our little side lengths, okay? So now I want to go label some points. So let's go add, let's say this intersection's here so we know what we're talking about. Let's call it C, and let's call this one A, D, okay? And then actually this intersection right here, let's also call that an E. Now what do we know about length AE? Well, AE has a length of 1, that height of 1 right here, okay? Just like it does on the ends. So we know that has a 1. We know that we have, well, a radius, OB. OB is our radius, right? OB. And let's call that R. We don't know what that is. We have a little R going on here. Well, AO is also our radius. AO is also the radius here. But then how can we label EO? EO would be that radius minus the 1 because AE was 1. So EO is our R minus a 1 here. So if EO is an R minus 1 and OB is our R, what is EB equal to? EB is going to be R plus R minus 1, which is a 2R minus 1. So again, that's this length here. 2R minus a 1, okay? Let's deal with that subtraction again. Let's go actually draw another little radius here. Okay, it's going to be perpendicular to the corner. Again, tangent to a circle theorem, we're going to apply here. Right here, it intersects right there, and it's perpendicular, and we have an R here, and this helps us visualize what's the length of CE. Okay, well, if this length here is a 2, because it's a, well, a rectangle, CE would be a 2, or R, excuse me, misspoke, would be R minus that length of 2 because it's equal to this length, R minus a 2. Same thing happens here. We have a 2 right there, and so we have an R minus a 2 here. So those R minus 2 is the length of CE equals an R minus a 2, and an ED is equal to R minus a 2, okay? And then after this, we will apply the intersecting chords theorem. If you remember what that is, if we have a little 2 chords that intersect in a circle, A, B, C, D, they tell us that A times B is equal to C times a D. And we actually have enough information to apply that here, okay? So chords, again, within the circle, be careful at the end. So A, let's go this first one, A, let's call 1. So we have a 1 times the next part of the chord, and remember intersections right here. So AE is a 1, let's go, I'll write underneath it, AE times AEB, so you can see it, EB is equal to, it's gonna be a CE times an ED. Okay, so we have 1 times a 2R minus 1 is equal to a CE, R minus 2, times ED, again, R minus a 2. And this is actually beneficial because look, now we have one equation with one variable. We can solve for that variable. Well, 1 times anything itself, so we have a 2R minus 1 here, is equal to, let's multiply this out. We have R times R is R squared, minus R times minus 2, we have minus 4R plus a 4. Let's bring everything over to the right-hand side here. I'm gonna subtract 2R, and I'm gonna add a 1 to our like terms, and we have 0 is equal to R squared minus a 6R plus a 5. Now, luckily for this factor, so don't need to go to quadratic formula yet here. We have an, well, R here, what multiply it to be 5, but adds to be negative 6, minus 1, minus 5, meaning my two R values, radius, is 1 and a 5. Well, how do we have two different radius values? Well, one of these makes sense and one doesn't. Let's look at 1 first. If radius is 1, is that even possible? This length from A to E is 1, so that there's no way that O to A is equal to 1, because what's this length here from E to O? So we can eliminate 1 and use radius of equal to 5 here for our answer. So again, area of a circle here, area of the circle looking for, area is pi r squared. So pi times a 5 squared. 5 squared is a 25, so our area here is 25 pi units squared, or approximately as a decimal, 78.5398 units squared, but I prefer in terms of pi. So again, our area here is 25 pi units squared. Did you get that answer? If you did, way to go. If you didn't, I hope you learned something here. And if you did learn something, make sure to like this video and subscribe to our YouTube channel. This helps us make more of these fun math videos for you and for everyone else. So as always here, thanks for watching.